Hello, my name is Slough, and I am a principal application scientist here at TA Instruments. And I'd like to welcome everyone to my webinar on enhancing battery safety through material characterization. So battery safety, especially with lithium-ion batteries, is a very active area of research. Lithium-ion batteries especially are prone to thermal runaway events, which can be caused through abuses such as mechanical, thermal, or electrical. For instance, in an accident, if a battery is punctured, the chemicals on the inside of the battery can contact atmospheric conditions such as oxygen and water vapor, and that can cause unwanted reactions and thermal runaway. Or if there's a poor control system with the car that doesn't adequately control the temperature of the battery pack, its temperature can also rise, again leading to thermal runaway, and then the concomitant pressure increase in the battery, which could lead to explosions and/or fire. So this is a very active area of research, and thermal analysis equipment is very critical to the study of these battery systems and battery safety. So I'm going to talk about two different types of thermal analysis equipment today. The first will be thermogravimetric analysis. For those that don't know, a TGA is an instrument that measures weight loss in materials as a function of time or temperature. A sample is suspended from a microbalance into a furnace, which controls the temperature of the system, and it's either ramping or isothermal. And some of the things that TGA can tell you are things like thermal stability, which is stability of a material within an inert atmosphere, such as nitrogen or argon. Can also talk about oxidative stability, which is stability of a material as it's exposed to oxygen. These pieces of equipment are very good to add spectrometers such as mass spec or FTIR to them, because then you can understand the chemical nature of the gases that are evolved during the experiment. And you can also study kinetics of decomposition and potentially understand lifetime of material components. The second piece of equipment I'm going to talk about is a differential scanning calorimeter. Now, this is an instrument that measures heat flow into or out of a sample as a function of time or temperature. So when heat is flowing into a sample, we call that endothermic. When heat is flowing out of a sample, we call that exothermic. And this instrument is good for looking at transition temperatures, measuring heats of enthalpy, whether they're endothermic or exothermic. It can study kinetics, and it can also tell you things about specific heat capacity of a material. So on this slide here, on the left-hand side, I have a schematic of a typical lithium-ion battery. Moving from left to right across this image here, on the left-hand side, we start off with the anode, which is basically a copper film, which has been coated with a graphite material, graphite slurry, which contains other chemicals in it, such as a polymer binder and some conducting additives added to it. We then come to the electrolyte, which is typically a lithium salt that's been dissolved in some organic solvents. There's typically a polymer separator, which is used to electrically separate the anode from the cathode. The separator can allow lithium ions to pass through it, but it will not allow electrons to pass through it, thereby providing the electrical separation that's necessary. And then we come to the cathode, which is typically a lithium metal oxide material, again, a layered material like graphite, which allows the lithium ions to intercalate into the interstices. And this is also coated onto an aluminum foil as a slurry, again, having polymer binders and some other conductive materials in it. Along the bottom, we see some of the things that can be thermal safety challenges within these batteries. I'm not going to go through every single one of them here, but starting at the low temperature end, there is the decomposition of what's called the SEI layer. That's the solid electrolyte interface, which is something that develops as you initially charge cycle the battery. It's a protective coating that ends up coating onto the anode. Further up in temperature, there's the shrinkage and decomposition of the polymer separator, which I spoke about. Loss of that will induce short circuits through the battery. thereby increasing chemical reactions and increasing the heat. And then on the high temperature end, we actually have degradation of, say, the electrolyte or the actual battery components that are sitting on the metal foils, the copper or the aluminum metal foils. When we use DSC to study some of these reactions, the materials are typically put in high pressure capsules. You can see that there's an image of one right next to the DSC here. We put these in high pressure capsules so that as the heats are evolved and as materials are decomposing, they're not allowed to escape through the pan, and thereby we capture the full heat of the decomposition or whatever chemical reaction that's happening inside of the pan. So moving on to some data here, I'm going to show a comparison between graphite and what's called NMC. The NMC is a cathode material. It's lithium, nickel, manganese, cobalt oxide. And then we have, as I say, the graphite on the left-hand side. Both of these materials were part of a battery pack that was charged and discharged several times and then finally left in a 100% charged state. The battery was taken apart inside of a glove box, and then the materials, the graphite and the NMC, were scraped off of their respective metal foils, washed with a solution to remove any electrolyte that was still left on them, and then sealed into the high pressure capsules. And then they were run in the DSC. So you can see from both of these, there is exothermic activity happening in both of them, but the energy difference and the character of the exotherms are quite different. On the graphite side, we have about 300 joules per gram of energy released. On the cathode side, though, we have about 1.6 kilojoules of energy released. And we see three separate exotherms there, dealing with three separate decomposition events. So once this battery begins to go through thermal runaway, it's the cathode and the energy released on the cathode side, the exotherms there, that are really going to drive the thermal runaway because it has so much energy is being released there. However, it's also interesting to know which of these actually begins to decompose first. So on the next slide, we're going to look at an overlay of this data, looking at the dotted line rectangular areas to see what we can tell from that. And so in this slide here, we see that actually it's the anode material that begins to decompose first. Around 82 degrees Celsius, there's an onset of exothermic activity, and that actually is the degradation of the SEI, or the solid electrolyte interface. So even though the cathode material has more energy release and a more complex transition, it's the degradation of the SEI early on the anode side, which begins to drive these reactions moving forward. And this type of sensitivity here to note, to capture the SEI degradation, you need an instrument that has very high sensitivity and a very good baseline, which is what the Discovery DSC 2500 does have. And then in this particular slide here, we show that we can actually study how these exothermic transitions are affected depending upon the state of charge in the material. So from this graph here, you can see that we, first of all, have an overlay of several different states. First of all, we have the NMC as received. So this is just as it comes in, hasn't even been put into a battery yet. And then we have the NMC left in a 0% charge state. So again, the battery has been through several cycles and then brought to a 0% charge state, disassembled, and the material put into the high pressure capsule as stated before. And then we have 50% and 100%. The 100% data is the data that you saw on the previous slide. And what's quite obvious here is that the state of charge has a huge impact on the complexity of the exotherms that you capture and the quantity of heat evolved. And on this right-hand side, we have a chart which shows that for the NMC cathode, we move from essentially there's no exothermic activity if on the as received material. And then we proceed through 72.1% joules per gram all the way up to the 1.6 kilojoules per gram. On the right-hand column, for comparison purposes, we have the data from the graphite anode, which is not shown on this particular slide here. But it just shows that in every situation here, the cathode is more energetic than the anode, sometimes by just a little bit, but sometimes by just a lot. So this type of comparison data is also quite useful and quite easy to capture on a DSC. Now I'd like to talk for a little bit about some of the challenges posed by these battery materials. And it revolves around the fact that many of them are sensitive to atmospheric conditions. That is, reactions with either water vapor and or oxygen. For example, the lithium hexafluorophosphate, which is currently the most popular salt that's used in the electrolyte, is extremely sensitive to water vapor. In reactions, it can release a very dangerous compound, hydrogen fluoride, or HF. Due to this sensitivity, most researchers not only prepare samples inside of a glove box, but they will also put their analytical instruments inside of the glove box as well. Now this is, of course, undesirable on a number of levels. It makes servicing the instrument more difficult. It takes up valuable real estate within the glove box, which could be used for other purposes, and just general interfacing with the instrument becomes difficult. With the high pressure capsules that I talked about previously for the DSC, again, two purposes there. I talked about the first purpose, which is to prevent gases from escaping so that you capture the full energy of the transitions. But also, once the samples are put into those pans, they are protected from atmosphere. And so you don't have to put the DSC, if you don't desire to, into a glove box. You can run those pans, you can take those pans outside of a glove box and run them inside of an ambient installed DSC. On TGA, however, it's a little bit more difficult because gases need to evolve from the TGA. You're looking at weight changes over time. So those materials have to be in open pans. Now, typically TGAs have certainly sealed pans which are opened prior to loading into the TGA. However, some of these battery materials are so sensitive to oxygen or water vapor that even the short amount of time it takes to load, to open them on the autosampler and then move them into the furnace of the TGA is enough to contaminate them. That's why TA Instruments is proud now to introduce a new TGA pan. It's the TGA Smart Seal pan. A picture of it is shown here on this slide. And it's composed of a T0 DSC pan, which has an aluminum foil lid. The aluminum foil is hermetically sealed to the T0 DSC pan using a standard T0 press once you've placed the sample inside of it. And this assembly then is put inside of a bale, which has a cutter mounted to a shape memory material, which once you heat it slightly will actuate and drive the cutter through the aluminum foil, thereby opening the pan. If I move to the next slide, we actually see the full assembly. So we have the pan and foil shown on the bottom, and you can see the cutter there, and you can see the nitinol spring in a circular pattern rotating upwards. So again, the sample is loaded in a glove box. Your sample is loaded into the pan. It's sealed in this pan, placed inside of the bale, and then this can be placed on the autosampler tray and then run as normal within a TGA. Once this pan is loaded into the TGA, we typically purge for a specific period of time in order to get the TGA furnace down to inert conditions. And again, raise the temperature slightly to actuate the nitinol driving the cutter through the aluminum foil. And then this TGA is run as normal. And of course, samples that are sealed within these pans can sit on the autosampler tray for extended periods of time. So obviously seal quality is of critical importance here. And so first I want to use a couple of slides here to demonstrate the seal quality for these pans. What I have here is a set of 10 runs in which a desiccant sample was tested inside of a discovery assay. So desiccant materials, they obviously are materials that will absorb water. So these materials were dried and they were sealed inside of the TGA Smart Seal pans, placed on the autosampler tray, and then run sequentially inside of the discovery assay. The discovery assay is an instrument that allows us to expose pans to specific temperature and relative humidity conditions. In this case, all 10 were left at 25 degrees Celsius and at 50% relative humidity for about 4 hours. So this mimics those conditions of 25 Celsius and 50% humidity, fairly well correspond to conditions that you might see in an ambient laboratory. In fact, many ambient laboratories are going to be less than 50% relative humidity. Now, the total test time here was fashioned so as to reach a full 48 hours or 2 days. And of course, if there's any leakage through the sealed pans, you will see this as weight increasing upwards because the sample is absorbing moisture. There is no indication of that for any of these 10 here. The seals here are hermetic. Now, with these 10 pans, we did a second experiment. We left them sitting on the autosampler tray for 2 weeks. We then loaded them back into the assay, and we compared the mass at the end of 2 weeks with the mass of the sample that was recorded at the very beginning of when they were loaded. And that's what the first 2 columns show here. The left-hand column is the initial mass of the sample when it was prepared, and the 2-week column shows the mass of the sample after it has sat on the autosampler for 2 full weeks. The middle column here shows the percent difference in mass. Everything is safely into the hundredths of a percent or even less than that difference. But it's the final column here which is most important, showing the microgram difference between the initial mass and the 2-week check. Everything is in single digits. For the discovery assay, the tear repeatability is plus or minus 5 micrograms, meaning that if you tear tear a pan and check its tear several times in a row, the tear value will be within plus or minus 5 micrograms. All of these samples fall within that. All of these samples show that they are perfectly hermetically sealed inside of these pans here. So the hermetic quality of these seals is actually quite good. Now I'm going to move on to looking at LiPF6 in these pans. So I want to first off review what the decomposition of this material is under dry and wet conditions. So if LiPF6 is dry, if it hasn't been exposed to water vapor, it will decompose into LiF and PF5. Under wet conditions, LiPF6 will decompose to LiF, but it will also decompose to POF3 and HF. And the PF5 that happens, that is produced during the main decomposition event, can also react with water and produce those same 2 components, the POF3 and the HF, when it decomposes as well. So we took 3 samples of LiPF6 powder, we sealed them in the TGA Smart Seal pans, placed them on the autosampler. We ran 1 sample immediately, we ran 1 sample after 24 hours, and we ran the 3rd sample after 48 hours. From this, you can see a single weight loss event is captured in all 3 of them. The reproducibility is excellent, and there's no indication that the decomposition is changing over time. Therefore, no indication that these samples are being exposed to any type of water vapor. So again, we see that the hermetic seal quality here is excellent, and these samples are staying in the dry state during decomposition. And we can further confirm that by connecting an FTIR to the TGA and looking at the spectrum. So this spectrum that's shown here, this is an overlay of all three spectra that are obtained during the maximum rate of weight loss in the TGA scans. We can see the overlay is excellent, and what's captured here is the PF5. So this confirms that this material is dry, and that's all we're seeing here is PF5 being decomposed. And this actually points out another excellent thing about the TGA Smart Seal pans. Because you're not having the TGA inside of a glove box, it's very easy to connect a spectrometer to it. If your TGA is in a glove box, you either have to put the spectrometer in the glove box with it, or you have to figure out some way to pass the heated transfer line through the glove box wall. Neither of them are easy or desirable solutions. Now, we compare this against a second example where we have taken 2 samples of LiPF6 powder and we've deliberately exposed them to atmospheric conditions of water vapor. One we exposed for 30 seconds and one we exposed for 5 seconds. So the 30-second sample somewhat mimics if you had a sealed TGA pan and you opened it prior to loading into the TGA furnace. The 5-second is obviously something where you are making as quick of a load into the TGA furnace as humanly possible. And we can see here that even as fast as 5 seconds, you can tell through the TGA data alone that this sample, this material has been contaminated by water vapor. There is a second transition that's occurring now below 100 degrees Celsius, which again is not apparent in the dry material. And we also see here that the weight loss onsets for the main decomposition are somewhat slightly depressed. Remember, for the dry material, everything was laying on top of one another. The reproducibility did not show any of that. Now, again, if we take a look at the FTIR spectrum, and this would be from the 30-second material, now we see, and this is during that first weight loss event, now we see HF, and now we see POF3 captured in the FTIR signal. Again, confirming that yes, LiPF6, when it is exposed to water vapor, will produce these 2 components. So this actually shows that the TGA Smart Seal pans are great to use for studying battery materials or other atmospheric sensitive materials. So in summary, I'd like to say again that battery safety, it's a critical research area, especially for lithium-ion batteries. The DSC can be used to determine a number of things, among them onset temperatures for your reactions that you capture, the enthalpies, or the amount of heat that's evolved during these exothermic reactions. And you can do studies that track variations of these reactions, for example, as we showed with state of charge, as a variation state of charge. On the thermogravimetric side, TGA is an excellent tool to examine degradation of these materials and to study the chemicals that are emitted when coupled to a spectrometer, so that you can capture whether you are emitting any types of dangerous chemicals or chemicals that are highly reactive that would tend to drive the reaction even further. And finally, the TGA Smart Seal pans provide researchers with an easier way to analyze atmospheric sensitive samples, such as those found in batteries. We will now take about 10 minutes to answer any questions you may have. Please submit any questions that you have in the Q&A box, and we'll try to answer as many as we can. And I thank you for listening.
Thank you, Gray, for that great presentation. We now will take a look at questions. Please remember to continue to submit your questions through the question box. Our first question is, how can manufacturers integrate thermal analysis techniques into their battery development process to enhance safety?
Okay, thank you. I'm hoping everybody can hear me, and that's a great question. I think thermal analysis can help in a number of different ways here, and I think we kind of just touched on it a little bit in the presentation. It can certainly help look at individual components that go into batteries, such as just studying the cathode materials or the anode materials or the electrolyte materials in isolation. And you can do that across a number of techniques. One thing I didn't touch on is you can use also thermomechanical analysis to study the separator within the battery. So that's another thermal analysis technique that can be integrated into the study of batteries. But looking at components in individual and then looking at them combined together also. Some researchers will together layers of material to form somewhat of a mini battery to analyze them within the DSC pan itself. Or as we saw here, you can use thermal analysis to study how things change depending upon changes in the material themselves. So state of charge was shown as an example here, but you can also look at modifications to the materials that you're going to be studying. So maybe you have slight composition tweaks that you make to your materials, and so you want to make a comparison across different materials that have slightly different chemical compositions. And thermal analysis is a great technique to track those types of changes.
Thank you for that answer. Follow-up question. What strategies can be employed to mitigate the risks associated with thermal runaway in LIBs?
Okay, so again, my background is not fully into lithium-ion batteries, but I think that some of the strategies that are being pursued by researchers in the field are looking at different types of materials. So they're trying to move away from liquid electrolytes and more into solid electrolyte materials. So there's going to be material changes, and that's where they're really looking, I think, to try to mitigate the risks of thermal runaway. And also, by doing these material changes, you want to get to the point where degradation temperatures, the onset of degradation, is pushed to a higher temperature. Here we saw, for instance, that the anode material was the first material. The degradation of the SEI layer was the first material to begin to decompose, and that was at 82 degrees Celsius. And so battery must operate at a temperature below that and well below that. Typically they're trying to operate them at 60 degrees or something like that, around that temperature. So if you can push that initial degradation temperature up higher, then that would be a goal in terms of making batteries more safe. And that's going to be some type of material change, again, moving from liquid electrolytes to solid electrolytes, or if staying with liquid electrolytes, having them be something that will begin to decompose at some higher temperature.
Fantastic. Another question is, was the effects of state of change examined for the anode as well?
Yes, now I did show the table, which gave a comparison, but I didn't show the graph of data itself. But yes, we did look at, not only did we look at the cathode material and looked at the variation state of charge. That was part of the actual data. But if you go to the application note, you will see that there's also a graph of the anode data collected at various states of charge as well. The same exact states of charge, so 0, 50 and 100%, and also the as received material too. That data just wasn't shown in this particular presentation, but it is there in the application note. And I encourage people to look at the application notes that we have online. And there will be, with the self-opening pans as well, there's going to be application notes coming very soon. They'll be on the website for people to download and take a look at. So keep your eye open for new application notes that deal with the self-opening pans as well.
Fantastic. Our next question is, how early in the battery development cycle should thermal stability testing be integrated, and what best practices can be followed to predict long-term thermal behavior?
Okay, so I would say that very early, as you're developing materials, you probably want to begin to understand what is their degradation temperature. Begin using both TGA and DSC very early on. Again, looking at as new materials are developed, looking at them in isolation, which I had stated as in part of the answer to a previous question. Doesn't have to be part of a battery yet. It can be just looked at. So you have a new material that's going to be used as a cathode material. You can begin automatically looking at the stability of that material under inert conditions right away. I would integrate that very early on in the process, and as you begin to make develop batteries, again, the thermal analysis can really be used, throughout the development cycle. So I don't see where you can't start early enough in using thermal analysis. As far as best practices, predicting long-term thermal behavior, that begins to get into areas like kinetics, which you can do both with thermogravimetric analysis and with DSE, with differential scanning calorimetry. You can study kinetics of materials. With TGA, you're basically studying the stability kinetics. You're understanding, how the degradation of the material may shift with temperature and the rate of decomposition. You can calculate something called a lifetime plot, which allows you to understand how long a material might be stable at a particular temperature for a particular period of time. In DSC, you obviously are looking at the kinetics of the reactions that are occurring there. And all of these kinetics studies, whether it's thermogravimetric analysis or DSC, allows you to, once you have the kinetic data in hand, not only do you get things like activation energy from the analysis, but you also can plot predictive curves so that you understand, again, how the reaction rate may change with temperature. And again, that would guide you in terms of what's the upper temperature limit for a particular battery that you want to kind of stay below. So I hope that as far as best practices go, doing kinetic analysis in addition to looking at onsets and degradation, those are some of the things that would be best practices here.
Thank you so much again, Gray, for a great presentation and for answering these questions. And I want to thank everyone again for joining us. Just a reminder, there will be a recording of this webinar, which will be sent out to your email in the next day. And don't miss our next webinar, Accelerating Battery R&D through Inoperando Isothermal Microcalorimetry, next week on October 16th. Register via the link in the resource box, and please contact TA Instruments with any additional questions. Thank you very much.